Good afternoon, respected Uma ma'am, Imon sir, and my dear fellow mates. We are here to present our third year project, a third year project report. This is Abhishek Karmakar, and the rest of my teammates are Pushkar Sahai and Satyam Gulshal. The project on which we worked on is titled as Classification of Roads and Buildings from Satellite Images, and in this we have used this computer vision and image processing approach. We have used various image processing techniques, various algorithms has been used, and also at the later part of this project we have also trained a model on CNN and it gave it an accuracy of 92%. Okay, so let's just move on. This is a Landsat image of North America on which we worked. It, it clearly comprises of the urban area, the water body, the forest region, the land, the road, the buildings, the stadium, everything. It comprises a perfect image in which every details of for classification it needs to be. Okay. So in this project what we did is we have in machine learning we have used four approaches, and they comprised of ORB. The first one, the second one was the bounding approach. The third one was a watershed algorithm, which clearly separated the urban areas and the rest of the region. And the fourth one was Douglas Pecure. The Douglas Pecure mainly it extracted out all these values, means we could just clearly visualize each and every portion of the roads and buildings. So what we did, we just combined both of them. We have combined the watershed and the Douglas Pecure so that we could get a better visualization and the image segmentation can be done in a better way. Okay, and the later part, when we have got the idea, when we have clearly found out the buildings, the roads, then we have extracted them out, we cropped them out, and then the model was trained on that, which gave us an accuracy of 92%. Okay, so let's move. We will start from the ORB, oriented fast and rotated brief algorithm. This ORB is basically a key point detector technique, means it's a corner detection technique. It uses the two algorithms. One is the fast and the second one is brief. Basically, ORB works with a combination of these two both. ORB is a key point matching technique, and key point is supposed to be told as a point of interest or a region of interest. Mainly, if in a technical way, if I'll tell you, it's a small region in image that's particularly distinctive. Means the region of an image where the intensity variations takes place. Means the intensity, wherever the intensity variations takes place, it need to satisfy some criteria, and if it do so, then that is known to be a key point. So fast algorithm is used to detect the key points, and brief algorithm is used to find the it's a descriptor basically, so it describes the key point. We haven't used this brief, we have only worked in fast because this fast was just to use the key points, and key points has been used in order to detect the buildings and roads. The first approach which we thought of is, why don't we just take the key point of each and every building and road, and then if suppose picture is given, we just gonna match it whether this key point is present there or not. We could be using this brief algorithm, this description of that key point, in order to fetch the details, but then it 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 didn't work. So brief wasn't used in this case. We have just used fast, and we have proved that fast using ORB it's not a correct technique, so we have switched on to the bounding approach. Okay, so why didn't this work? Let us start with. So key point, as I've told you, it's nothing but it's an area of certain pixel intensities around it, and it considers the pixel brightness around that area, this fast algorithm, and basically the key point is where the intensity variations takes place. I've told you. So fast algorithm, what it does, it calculates the key points by considering a pixel brightness around that area. A pixel is there and 16 pixels are surrounding it. Let's change it. See, these are the points which these are the steps which we have followed in ORB. Each point is described in brief. The first one is that we just load the image and then we convert it into grayscale, and for we need to specify of how many key points do we need to find. We have found 1,000 key points, we could be using more. And then finally the ORB method was used to detect them, and then we just plot them on the input image and we stored it. So how did we do so? How did we find this ORB? How this fast algorithm came into existence? Let's move on. So what does fast do? It just considers a pixel, and it surrounds, basically that pixel surrounded by 8 other pixels. So what it does, it considers a radius of 2 and it checks all the 16 pixels around it. So what it does, it compares the brightness of that p with the remaining 16 pixels. This, if brightness is said to be a pixel is said to be of high brightness if this these pixel values, if it's greater than IP plus H. This H stands for threshold value. If suppose this pixel has the value, its intensity is greater than IP plus H, then it's said to be a brighter. If it's less than IP minus H, then it's told to be darker. And if it lies in the range between IP plus H and IP minus H, then it's called to be similar. Okay, so what it is, out of the 16 pixel, if more than 8 pixels are darker or brighter continuously, then it's said to be a key point. It's the present one, 8 pixels has been taken, but early in the documentation it has used 16. So why, sorry, it has taken 12. Now it's 8, but earlier it was 12. So why 12 and what it is? So we'll describe it. Okay, basically, as I've told you, it's nothing, is key point is nothing but it's a feature detection technique, feature detection method. So we just take this pixel, this p1, okay, 16 pixels surrounding. So if we take this one, so obviously it's brighter, means IP plus H, this value is greater. And obviously for 5 it's also greater, and for 13 it's also greater, means all these remaining values, these are brighter, and this is contained to be darker or similar. I think that these are similar, of course. Okay, so I've told you that one pixel is surrounded by 16 other pixels, so let it to be x, and let p tends to x. This is supposed to be intensity. Okay, so if it's less than IP minus, then still to be darker. If it's between IP minus and IP plus, then it's called similar, and if it's greater than, then it's called brighter. These are the 3 states. So this fast algorithm is why it's supposed to be still fast, because each time whenever you are facing, whenever you're taking in a pixel, and every time you are just comparing one pixel with 16 other pixels surrounding it, will take a lot of period of, means it will take a long time. So a fast speed test has been checked first, and then a segment test has been applied. Basically what segment tests do is, a pixel has been taken, okay, whose intensity is IP, and we need to select a threshold, appropriate threshold for it, and 16 pixels are surrounding it. So as I've told you, it will check the brighter or it's darker, and if it's greater than or equal to 12, then it's considered to be a key point. But do we need to check each and every pixel every time? So for that, what it, a high speed test is done first. What it does, it checks only 1, 5, 9 and 13 pixels only. Okay, this 1, 9, 5 and 13, only these 4 are compared. What it does is, the first one and ninth one is compared first. If these two are compared, okay, I5 and I9, sorry, I1 and I9, if these two are compared, when first and ninth number is compared and it lies between this range, means it, if it's similar, okay, this, if it's similar, then that point is disregarded and next pixel is considered. But if it's not similar, then what happens is, um, it checks 5 and 13. Okay, so if when 5 and 13 are checked, so total 4 pixels are checked now in this case, 1, 9, 5 and 13. In this 4, if any of the 3 are, if they are darker or they are brighter, then it's told to be a corner. Then it will go for the segment test. First it will check these 4 pixels, okay, these 4 pixels, 1, 9, 5 and 13. If they are satisfying, then they will go for checking the 16 pixels over there. So this is the fast speed test, means every time, instead of checking the whole 16 pixels, it just compares the 4 pixels, and if it's greater, then it will consider it. Let me give an example of it, of that. If suppose it's a pixel p, and it will check what 1 and 9, this is brighter, this is darker, or it's similar anyway. So when they are not lying in this range, both of them, when I1 and I9 are not lying in this range, then P is not a corner. It has been disregarded. I mean, then the second test is taken, 5 and 13. Now what it does, 5 and 13 are checked in this case. So in this what happened, 13 is also brighter, 1 is also brighter, and 5 is also brighter, because it IP plus T is its intensities, this intensities of 13, 1 and 5, these are greater than IP plus T. So of course these are brighter, hence it's considered to be a corner point. So now what it will do, it will check the remaining 16 pixels. So in that case, a fast algorithm has been used in order to find the key points. So after using these key points, these are something which are plotted on the image, but since they are not very clear, so a circle has been plotted in that case. This radius depends upon the intensity, the number of pixel values which are similar, the n and continuous values, whether they are darker or they are brighter. So we could clearly visualize it, because since there are many values like over here, and then over here means we have just ignored it, we just couldn't find it, where are they. So I've just plotted in the circle format, so that we could just clearly visualize it. Okay. So ORB, the main disadvantage of this ORB is, see, here values, there are no key feature which are found, no key point which are found in this region. Even in these region, there is no key points which are found. So even so, the point which we have considered first is that if there is a building present, we could extract out the key points from there, and we're going to check in this image for every different image, the road structure, the building structure will be different. So the ORB can't come into existence. So ORB is just totally disregarded. I mean, this is none of our concern. So we have just disregarded this, and we have moved on to a second approach, which is called bounding approach. Bounding approach, in the initial step, what we did is, in this bounding approach, we found out all those points, or those curves or patches, whatever you'll say, which have the same color or same intensity. Mainly, what we are gonna do, we just convert it into a binary type, it means black and white, and then we are going to extract the white portion from the black background. So we see the image which was shown at the first page, that was a very high resolution, and that was a the size of that image was very large. So we have first downsampled it, so that the processing can be taken could be take place easily, and also fast. So we have first downsampled that image, um, and then we've converted it to grayscale, and then a threshold value of 127 has been applied to turn it into black and white. Maybe 127 is just half of 255, for which it worked perfectly, but I've also checked for rest of the cases, and for 127 I got okay, this is good. So after it's converted into black and white, we have identified those regions. So it appeared something like this. But do we get a perfect result? No, obviously, because if you see over these regions, or these forest regions, this one, what happens is we get those values which are not even of a concern. Means those forest region, maybe those are rocks which we have extracted them out, and every time a building can't be of high density. I mean, mm, those regions, it's not mandatory that it need to be white always. So, and even it's white, it's totally not that that's a building, that can be a rock, that can be a something else. That's means just extracting this white value, this is not a good approach. So we moved on with this. We again moved on with that. What we did, we found the coordinates of each curve, and then we plotted them. For each curve, what we did, we suppose this curve I'm talking about, for this case we are talking about, we found the x comma y, the initial value, and we found the width and the height of that curve. So after that, so what will be the coordinates of that? This will be x comma y, this will be, since the width is w, so this will be x plus w comma y, this will be x plus w comma y plus h, and this will be x comma y plus h. So when we have plotted the, we have got something like this. So it simply looks to be like something called clustering. Those buildings and those roads, um, we have got it, but we actually thought of like if we get some curve, we can grab them out, we can take them out and we can plot them like these are the buildings and these are the roads. Obviously in this like in the previous one, we have got unknown values, like where the regions where there were rocks, where there were no buildings present, wherever there were white portions that got plotted out. So in this case it doesn't happen. When we have got these boxes, we ran a for loop, and every time when we first for the first time whenever we counted the curve, we just plotted them. So an outline of those curves have been plotted. So in this case what happened, even there is a small dot and small portion which has been extracted. In this case there are many of them. So what happened is the x comma y value of these boxes, x comma y value, and after the width or height has been found, it's something what happened, they got, if the white portion is very small, if there is just a dot, the x comma y, or these four coordinates whichever there, these are very small, means the boxes are very small, or they are something like equal. So those have been discarded over here. See, there are many points which have been found over there, but here it has become less. Okay, but still in these regions, if we want to see, we haven't got it, we haven't just reached our goal, we could not found out the buildings or the roads in these. So this this won't work. So what can we do? We just thought, and then we got a result. We thought of a idea, like why don't we just segregate them first, why don't we just divide the image? We first we extract the area where there are roads and buildings, mean the urban region, wherever there is an urban region, why don't we just take them out where the density of buildings and roads are quite more, and separate out the region where there are concrete residences below, or the region where this forest or water are there, we just don't want them. Why don't we just take them like this portion where there are forest, where there is water, we just why don't we just disregard them, why don't we just leave them out, and then we can work on this urban region. So in order to take this urban region out, we have found out a method, we have used a method called watershed. So this watershed algorithm is nothing but it's something called two low-lying areas, or one low-lying area and one high-lying areas. These used to make a ridge in between. Suppose there are two catchment basins are present. Just visualize it. There are two catchment basins are there. One is this one is this one, and whenever a drop of water is falling in between, there is an equal probability that it will fall in this one. It can fall in this one, and it also can fall in this one. I mean, there is no boundary which has been made. There is an equal probability of falling in both. Or you can say there are two low-lying area, and we want to divide them. We want to create a boundary of the two low-lying area. We just want to see. So watershed algorithm works in that case whenever there are objects which are touching each other, or they are overlapping each other. So watershed algorithm works in that case. When an image has been provided, it converts into a grayscale, and it can be viewed as a topographical image in watershed algorithm, the basic structure of it. And the regions where there are high intensity or high pixel values over there, whether so it considers that to be peaks and hills, and where there is low-lying areas, it denotes them with valleys. The low-lying valleys, what they did, according theoretical concept, using a philosophical concept, what it does is, if there's a low-lying area, we need to fill the water, we just fill it and fill it, and at the time comes when it it comes to just fill the low-lying area and comes at a level of this high level area, means it just submerged the low-lying area. At that point of time when both of them becomes equal, a ridge is created in between. Means at the point when the low-lying area and the high level lying area becomes equal, we found out like this is the final part. So a barrier has been made in that case. So that's the main concept behind this watershed algorithm. So this watershed algorithm is also called a marker-based watershed algorithm because it gives different labels to our objects. We first found out the foreground area of some intensity, label that region, and when we become sure of the background region or the non-object region, we fill them with 0. This is our marker. Okay, 0 and 1. The background is filled with 0 and the foreground of the objects is filled with 1, and then the boundary, this number has been applied by us. We just mark the boundary with -1. That can be filled with anything. We have just changed this watershed algorithm, this and that. We just according to our necessity we did it. Okay, so these are the things which have been used in this case: binary conversion of the image, we use distance transform, we have used morphological X transform, and then we applied markers. The applied markers I've told you, but there is a modification has been done in that case. The background has been marked with 0 and the foreground has been marked with 1. Let me explain you this watershed using this image, because it's after all, this image has also been considered to be like a topographical image in this watershed algorithm. I'll explain you this whole watershed algorithm using this image, and then the image which I've used, the Landsat image which I've used, I'll explain it using that. Okay, these are the terms which I'll be covering. These are the key terms actually. Okay, so this watershed algorithm, what we are gonna do, the first thing which we are gonna do is we just change it into a black and white depending upon the threshold. So okay, this is the image. So if there is a white portion, if we want to convert it into black, these are the objects. So these objects are greater than the threshold value. So obviously this value would, we want this value to be marked with different, and we want this value to be marked with different. So since this value is, if we do the binary conversion in this case, so what will happen is that this will be marked with black, and since the threshold value of this white is greater. Okay, so since the threshold value of this white is greater, so it will be marked with white, and the threshold value of this is low, so this will be turned into black. So we just did the inverse. We just did the inverse. Means if the threshold value is more, that will be converted into white, and if the threshold value is less, that will be converted into white, and if the threshold value is more, that will be converted into black. Just the inverse of the binary inversion of threshold binary inversion. Okay, simply what it is doing, if the threshold value is more, it will be converted into black, and if the threshold value is less, that will be converted into white. That's it. And you can apply any of the binary conversion methods, anything, Ostuz, binary inverse, or Tozero. I'll prefer not to use Tozero in that case. Okay, binary and using Ostru, that's both of them are good, or you can combine them. Anything can be fine. So binary, what it does, this white value, this after all is a binary image, so this white value is 1 and this black value is 0. Here is the key term. Okay, the second thing which we did is we removed the noise from the image using this morphological X transform. This morphological X transform, there are many processes in this morphological X transform. We have used only two. One is the erosion and the second one is dilation. Erosion is this, that the size of the image is reduced, see, and the dilation, the size gets increased. Simply, since it's a binary image, so the boundary pixel, means boundary value 1, it's deducted, it's removed. These boundary 1 values, these are removed. Okay, say only the inner portions are remaining, so therefore it appears to be something like this thin. And in dilation, what dilation means to become a little bit of larger. So in this, what it did, on the boundary, if there is a 1, so in the corresponding neighborhood 1 has been added, so therefore it becomes a little bit large. See, in the matrix transform, if there is 1, see there is 1, so in the neighboring it adds 1. See, and here it will be 1 and here it will also be 1. See, it's here it's 1 and here it's also 1. If it's suppose in case of erosion, it will be this 1 will get deductive. If it's 1, so in dilation, what it will be, it will be 1, it will be 1, it will be 1, it will be 1. So in that case it will just getting expanded, that's it. And in erosion it will just get removed. So this open morphological transform comprises of two methods. One is called erosion, second is called dilation. So in order to remove the noise, this opening method has been used. For the first time it's done erosion, so after the erosion has been done, when 1 has been removed, it totally becomes black, 0. So this size is also this was also getting reduced like this, it's also getting thin. And after, when again dilation is done, so when dilation is done on this, it becomes similar like the original image. Okay, so when the erosion and dilation has been done in this, the noise, all those noise, small noise, these are all removed and we get a fresh image. This is what this opening method is doing in for removing the noise. Okay, and for dilation result, we obtain the most certain background, and for foreground we're using distance transform. Okay, see, let me explain first the key term. What's distance transform is? Distance transform is nothing but except the boundary values. The inner values of 1, it will get changed. Like in this, it getting 2, it's getting 2, 2, 2, 2, and this will also become 2 because from this boundary, so this will become 2, and since it's near to it, so it will become 2. It's near to it, so it will become 2. Since it's also near to it, so it will become 2, and from 2 it will be 3. It's nothing but it's the distance of the closest boundary from each point. Like from the nearest boundary, this is the nearest boundary, right? So this is 1, this 2, this 3, so it's nothing but the shows the distance of the closest boundary from each point. From each point you can go to the closest boundary of how you can reach there. That is it. That's nothing more in distance transform, except when this distance transform has been converted from the binary image. When the distance transform has been converted, the result of this transform is a grayscale image, which looks similar to like similar because all obviously the dimension is same. So it's applied to on the binary image, and the result of this transformation is a grayscale image that looks similar to that input image. Okay, so if this is image, you can take the rectangle, like this is the matrix of this picture, and when the transform has been done, since this is 3 3 and this 2 and 1, so since it's 3 and it's a grayscale image output, so it becomes 3 is the brighter, and then the intensity decreases gradually from 3, then 2, then 1, and then 0. Okay, so this one, suppose this is the image, then after the distance transform, the output will be looking like this, and this will mean this, what the output will be looking like this. So why this distance transform has been used, let me explain to you. First, for removing the noise, we have used the morphological opening, the dilation, that erosion and dilation one. Then in order to get sure of the region which are center of the objects, means to, in order to get the foreground, um what we are doing, right, first let us discuss about the background one. For the background one, what we do is erosion, because after erosion the removes the boundary pixels. Erosion basically removes the boundary pixels, I've told you, no. In this erosions, the boundary pixels get reduced, so it becomes thin. This is the image. Now if we do the erosion, in this, we are getting see, this is the original image. There are two processes which can be done. One is dilation and the second one is erosion. If suppose dilation is done, then this is the output, and if its erosion is done, this is the output. If dilation is done, then the region which is this, we are sure that after dilation, this value 0, which is consisting of this is background. Okay, this region is the background. We are totally we are sure, obviously, we are sure that this is the value is 1, and the value which is 0 over here, or value 1 which is over here, we are still not sure that this is foreground. For foreground, what is done, if erosion is done in this case, so the size get reduced, and we are sure that this is the foreground. Okay, this is the foreground. So the similar kind of thing has been done. If erosion takes place on the boundary pixel, whatever is remaining, we can be sure that it's coin, or that's the object for erosion. Okay, but for foreground we are using distance transform. Okay, we are not using this erosion. For foreground we are not using erosion. For background we are using dilation for sure, but for erosion, for foreground we are not using erosion. The reason behind is, if the objects are not touching each other, if the objects are not touching each other, then if we use erosion, then we are sure that this is the foreground. We are damn sure. Well, we are just sure that that's the foreground, because the value which will be 1, that's the foreground. We are damn sure. But if the values are suppose touching each other, like in this case, if the objects are touching each other or they're overlapping each other, then like this is one circle and this is one circle, they are not touching it, there's a gap in between. So now if erosion is takes place, this is a foreground, this is a foreground, we are sure. But if this is the image and this is the image, both are overlapping over here, and now if again the erosion takes place, this becomes size small, this also becomes size small, there's a gap come in between, a discontinuity appears. So that's a wrong thing. That cannot be the point. Erosion cannot come into existence whenever the foreground, whenever we need to find the foreground. If the objects are not touching each other, for fine, in that case erosion can take place in order to detect the foreground. But if they are touching or they're overlapping each other, then this can't be erosion can't be a solution. We need to do the distance transform, because distance, using this distance transform, we are maintaining a distance from the boundary. We are getting the output, um, we are maintaining a distance from each boundary. So in this case, what will happen if the distance transform is applied, this is the output which we are getting. So if they're overlapping or they are touching each other, we at least we are getting to know that they at least there's a continuity appears in this case. Okay, so now if we appear the thresh if we use a threshold, we are getting the foreground value. So here is it, we are getting the foreground. So now we are sure that this is the foreground, and this is the background. This value 0 is the background, we are sure, and this is the foreground, the value 1, which is consisting of its the foreground. We have found it out. Now what we are do, what we are not sure of is the region which is the distance, this region which is surrounding them. Like this is the background which we have got it, and this is the foreground we have got it, but what about the boundary? This region we haven't found out yet. So if we just subtract this background from the foreground, we get this distance. So now what we do is, on the background we are applying the value -1, on the background we are applying this value 1, the boundary we are applying this value -1, and the remaining foreground we are applying this value 0. Okay, so these are nothing but these are the markers. After this markers, we are just replacing earlier what we did, that marker, the black background, that was value 0, and the white one, that is the object, that was value 1. So now the markers has been changed into 1, -1, and 0. Okay, so here is the image after the watershed has been applied. Here is the output. So the all the rural area we have got it. So, okay, in this case what happened is, this black region, as explained you earlier, this this white portion was the background and this became the object, because since the threshold value of this was less and this was more, Similarly, the threshold value of this was less, so that actually became the object, these became the object, and these became the background. So these value are 1, and that is a boundary, that's value -1, and these value which you can see, these value, these are the foreground, so this value is 0. Yeah, foreground with 0. So the next part we'll be discussing about the Douglas-Piquet method, what it is, and how we combined this watershed with Douglas-Piquet, and what result did we got, and how we used CNN. How did we achieve that accuracy of 92%? All will be discussed with all will be discussed by rest of my teammates. Okay, thank you.